Okay, thank you everybody for coming today to this virtual session of the OMLDS. This is a bit of an experiment that we are doing due to the current situation with the coronavirus crisis. Today we have a very pertinent presentation from Dr. Antonov about modeling the propagation of coronaviruses. I like to make an announcement too. We are preparing to start using a new chat platform, which is called Discord. It's very similar to Slack, and it will allow us to keep the community up to date and start conversations and have a more interactive approach. We stay using the Meetup site for announcements and scheduling sessions and events, but this will be a more immediate way of communicating. I'll be sending a message after the presentation with information on how to register and download and use this platform. As I mentioned today, we have Dr. Antonov doing a presentation on coronavirus propagation modeling. The presentation is structured in 3 sections. I'll be taking all questions through the chat, and we wait until the end of each of the sections to have Dr. Antonov answers the questions. Okay. So that being said, I'll let Anton proceed.
Thank you, Luis. Thank you for the introduction. I'm going to share my screen. So this is an outline of the tutorial presentation. So this is not just a presentation, it's a little bit more ambitious than that. It is supposed to be a tutorial. Before going through the parts of this mind map, it seems to be easier to have for this type of presentations and tutorials, having a slideshow is just not adequate. So that's why I'm going to be using a mind map, and we'll get oriented on this mind map for doing where we are at and what we are doing. I'm going to be having 3 screens. On this screen, it's going to be the presentations are going to be. On the second screen, you're going to see certain say diagrams, or like some sort of like, okay, let me bring a notebooks in which I'm going to be presenting a more substantial material. So if we ever go to the first screen, this is going to be for some other software or like web page search or something like that. So this slide, who I am. I do have a PhD in applied mathematics. I'm an applied mathematician. I was working in large-scale air pollution modeling, and that's actually quite adequate background for doing epidemiological models, especially on a large scale. This is what I'm interested in, how to do epidemics modeling on large scale. And after I moved to US, I worked for a company called Wolfram Research. They're the makers of Mathematica. They also make Wolfram Alpha. In the last 10 years, I've been branding myself as a senior data scientist, and I've been doing quite a lot of data science related things. So this actually brings me to my managing expectations part. This is not, although this presentation and tutorial is done for Orlando Machine Learning and Data Science Meetup, this is not so much about data science. It's very, data science is being used in a very marginal way for the models I'm going to be discussing. And the other is that I'm going to be accentuating on the certain methodological parts, and more about, it is more about how we actually model this kind of, when we encounter this kind of situations. What exactly we do with mathematical models? What would be the best way to do it? I'm going to present one particular way shortly. I mean, in a short manner, I'm going to describe some others. But statistics and data science are not the models which are adequate for this. So the other is that the presentation mostly is going to be done with Mathematica. I don't particularly, I don't think I actually, we've been trying to propagate my models into many other systems, but definitely I'm targeting R. At this point, the R implementations are marginal, but to a large degree, what we're going to see can be implemented from Mathematica or implemented from Mathematica to R. So there's because this is a tutorial presentation, I'm not sure what are the expectations of the people who joined. We had quite a lot of people who did not belong to the group or first timers. So I'm going to do a very quick overview of what we're going to be talking about, ideally in the first 5-10 minutes. And then we should be, you know, I mean, if you don't want to hear the methodological and didactical part, you can do something else. All right, so my first example, I actually opened this notebook. I didn't want to do any kind of real life examples about US or making predictions with real data and actual data, but in one of the forums which I frequent, it was announced that New York Times released this data set fairly recently, actually, like say 2 days ago or a day ago. So I did go to the GitHub here, and they do have I mean, they do have this data, and we can see they have been actively updating this. Actually, there's a new update with the new data from March 27. So I'm going to use this notebook here as an introduction. This should be live. So let me run it. I don't know to what degree people have heard or know about the coronavirus. This is definitely not the first repository in which data like this is being collected or presented. Probably the first one which I have seen is from Johns Hopkins Institute. They also have GitHub repositories, and they also have some live maps and some other stuff like that. All right, so what we see here, right? I mean, we basically, this is just for US, right? From New York Times. We see that we have different states and different counties in US, and for those states and counties, they have found what are the different cases of people who are infected and people who have died. So this is what we are seeing here on this geographical histogram. And I mean, you can see that the majority of the cases, if we do this, like look at this data here, we see that say 10% of the cases, sorry, 80% of the cases are in 10% of the counties. And for the deaths, this is even more exaggerated, like nearly 85–90% of the deaths happened in 10% of the counties. So I mean, this, and you can see this, but say New York, Seattle, you know, no, this is not Los Angeles, San Diego, sorry, San Francisco. I mean, they're like quite impacted. Here we see Chicago and so forth. I mean, these are things we would expect. What you see here, it's some time series, rudimentary time series analysis. The purpose of this notebook is to give an impression how to use this data, this a forecast. This is not what we are going to be doing. This is not a serious attempt to do forecasting. If this is your forecasting, for example, it's just not serious enough. It's you know, borderline, I would say, pathetic. So this is just as a warm-up to kind of see what the data is and what actually we're not going to discuss. I'm not going to be dealing that much with the data collection, data representation, whatever kind of forecasts you might have seen related to this kind of data analysis. The data analysis itself Of course, it's very important. And with the data analysis, let me go back to the mind map. The data analysis has to be done when we're actually looking into the general type of framework in which we deal with this kind of models. So what I'm going to be showing here is that we get a data from different sources, we massage it in some way, prepare it for our for what we are trying to do. We do certain data analysis. Based on the data analysis and our knowledge of the phenomena, we develop new models. And these models actually, they are supposed to go through different iterations. Obviously, we need to discuss models with peers, and this is actually, in some sense, that's why I'm doing presentations like this. And I'm having a team of people with which I discuss my models. So after certain models have been developed, we want to calibrate it. We want it to fit the reality better. And then we're actually looking into different scenario playouts. This is what I'm very interested in when it comes to making this kind of models. It's not just about predicting, but it's more about what kind of actions, what kind of steps we can make, or if we do certain steps, what is going to be the impact on the propagation. So you can see in this diagram, it's assumed that some of these models are time consuming to compute. So that's why the simulations based on the parameters selected from the different playout scenarios, the results of the simulations have been stored in a database, then they're visualized and presented in some way, and there's some decision making to be made. This is the general framework. Obviously, it does not need to be only for epidemics. It can be used for any kind of modeling which requires certain consideration, non-trivial simulation understanding of the process involved, and there's some trade-offs which different stakeholders and decision makers are supposed to make. All right, so the promised first example, and after which we can do something else, is it's probably this. Let me. All right, well, and unfortunately, this is animation which doesn't play. All right, so let's do it here. All right, so what we're seeing here. So I have a model which does propagation of, simulates epidemics on each of these squares, each of these little squares. I also have underlying traveling patterns from by air, traveling by air, by airlines. And you can see from this animation how a patient 0 who started somewhere in Seattle, like somewhere here, let's this cycle, I will see it, how this actually is going to propagate throughout the whole of US. And so, yeah, all right, so yeah, started somewhere here. We have patient 0 in Seattle, then through the different flying patterns and etc. The whole of US is undertaken. There are some scenarios here played out when we start the quarantine, and we can see also that if we start the quarantine too late, I mean, this is the, might have heard about this, the flattening of the curve. So if you want to flatten the curve, you need to actually start it within certain period. So I'm going to expand a little bit more on this. And one of the things you're going to, how this was computed, this animation here, this notebook here, the computations were not live, but they were prepared in this way. And I'm going to give a little bit more detail how the data was gathered. So we use certain data from the Columbia University, which actually was giving a very nice approximation of the population density over a regular grid for the whole world. So you can see it for the whole world and also particularly for US. And so from this, we used a particular splitting technique, geometry splitting called Voronoi mesh. This is the the Voronoi mesh being with logarithmic data, the points, the centers of this cells, they're the most popular airports in US. So here, these are the traveling by air patterns, the traveling from the different sites of US, from different ports. People who are in Florida, you can see Key West, Fort Lauderdale. This is, I guess, Tampa, Orlando, and so forth, right? All right, so here you can see, you can recognize probably Chicago, Atlanta. Here is Orlando. Sorry, Orlando is here. This is San Francisco. So we actually know what are the traveling patterns throughout US with this graph. We use a single site model, which is given here. This is just for one of the sites, for one of this little square I showed earlier. We actually simulate multiple versions of this, 167, and we extrapolate it in a certain way. We connect it with the traveling patterns, which you can see here, how this seed model has been extended. Then we do the simulations. We have around, say, 1,000 equations here, and then we make this kind of simulations. So for the rest of the presentation, I'm going to be explaining how, what is the particular methodology used behind this kind of methods, and what is this single site models, what are these multi-site extensions, and why we're doing it in this way. So I don't think Luis, I was supposed to have questions now? Or?
Yes, we have two questions. One is for Cassandra. She's asking about the name of the model. If there's a name for the model.
That's a very good point. No, I don't. I call it multi-site extension. Okay, like depends what you're talking about. But okay, well, first of all, I really don't understand. I mean, not aware where this question comes from. I'm going to go to my blog here, and so let me find. So I'm using the so-called compartmental models. These compartmental models being extended with something I called multi-site compartments extension. So basically, on each of this, if we take, if we look at the standard compartmental models in epidemiology, they're like SIR models. SIR means susceptible, infected, recovered. I'm using different versions of these models here, of the classical models here, and I'm extending them given some traveling patterns. The model itself, we haven't named it, but I do have some naming convention for the models I work with. There, for example, if I wanna, the SIR model I was talking about, just let me do this here. If I want to do the SIR model, right, it looks like this, and I can probably display it in some way, right? I mean, this is the simplest one we're talking about, because we have the way coronavirus and COVID-19 is. We actually, and this is what I'm going to be talking next, some basic knowledge about the coronavirus and COVID-19. The way they are, we have two populations which are infected, normally symptomatic and severely symptomatic. Because of this, these models have been extended. I also have, with my models here, I have also made extensions with, say, like this is probably the most complicated single site model. This is a model with, which follows quite a lot of populations. You can see we have exposed populations, two infected populations. You have the hospitalized population. And also I'm very interested in the medical supplies and hospital beds, what kind of restrictions we are going to bring into this. In my next, in the next part of the talk, the bulk of this is going to be discussing these equations and the paradigm with which they have been derived. Okay. Good question.
Anton, we have 3 more questions. For the sake of time, I'm going to ask the audience to refrain here. We're going to answer 3 questions and then go to the next section and answer more questions then. There is a question for Bill Kahn about the flattened curves that you show. He's asking if the area under the curve is the same.
Generally speaking, not. It depends. I mean, it really depends what are the scenario play out. I mean, if you have infinite lockdown, you probably can conjecture about this, but then you also, in the equations, how do you model the deaths? Do you model deaths only from the infection, or do you also model the deaths from the from just, you know, the general death rates? So it's not, I mean, it's an interesting question. I mean, we can probably use it as a verification procedure, but generally I don't expect it to be the case.
Okay. We have one question I think you would love to answer. What is the programming language that you're using for this?
Right. So as I mentioned, thank you, Luis. Yes, I worked for a company called Wolfram Research, right? At some point when I moved here, and for some reason it's very hard to get to Wolfram site for some reason. All right, so Wolfram, they make a product called Mathematica. There's a recent release with version 12.1. This is what you're seeing, version 12.1 of Mathematica. I have used Mathematica for more or less 20 years. This is not, Mathematica is very similar to R. If you know R, and if you know, you can become relatively quickly, not quickly, but relatively quickly a good programmer in Mathematica, and the other way around. Mathematica is more consistent than R. It's actually, especially for products, for problems like this, it's, you cannot do it with something else. We cannot do it quickly enough. So, right, this is what I was, yes, thank you for this question, and Luis, also thank you for bringing it up. Okay. So I'm going to...
We have one last question.
Yeah, go ahead.
It's from Bill Ken 2. He's asking if you recover, are you no longer susceptible? And I'm inferring this is as a part of your model. When in your model, are you taking into account that a person that recovered won't have the disease again?
Well, right. This is actually what we're going to be discussing next, right? How these models are going to be developed. You can see it here. So right, I do actually plan to discuss all this, right? So we're basically at some point down the road, I'm going to be discussing this. And yes, in these models, it is assumed that people who have been infected and survived it, they actually recovered, and they're not susceptible again. In a sense, they're a recovered population. That might not be true if the virus itself is mutating. I'm not particularly, I don't fully understand the question, but I'm saying there are certain assumptions here. But we have about these models, and the compartmental models, it's exactly that. The compartments, they have certain concept behind, or certain assumptions, how people move between the compartments. As I said, this is something I'm going to be discussing next. But before that, I want to mention certain basic knowledge requirements for the coronavirus. So I assume I answered the question, did I? All right. So here, this in this second part about the concepts, basically what I started already describing some of the parts here. I'm just going to give a quick overview of what the coronavirus is known about. I mean, this is something I collected from, say, a week or two ago. I started working on these problems in the beginning of the month. So the data has been changing quite dynamically. This here, in general, as I mentioned, this talk is much more about, making the violin, not playing the music. It's much more about the tools and the paradigms, not so much about making actual simulations. But of course, we need to be looking into actual simulations, actual data, and try to calibrate our models in order to see are we on the right path. So in the middle of this concept section, after like say 10-15 minutes, I'm going to be taking questions. So first, for the coronavirus, what it is known and what are the things we brought up. Just a moment. So we know more or less this is what has been summarized here, and I can zoom, if it is required, I can zoom this more. But we actually, we know that we have two types of populations. Around 20% of the population gets severely symptomatic. And the death rates, we have some estimates about the death rates after I have put this in. The different other kind of research was brought up. We need to be, we need to separate what is the virus itself, like SARS-CoV-2, and the disease from the virus. So to some extent, this coronavirus propagation, we're actually talking about the coronavirus propagation itself, but of course, this is also associated with a certain disease. The coronavirus can be propagated, but if you have vaccine or immune, if you're immune to it, or you just don't, you actually, even if you have it, you don't have the symptoms, you're asymptomatic all the way. This doesn't mean that the virus has stopped propagating. So there's it's an interesting question. What are the infectious rates, the infectious period, and what is the period in which we don't show the, this is when we talk about exposed population. So this is the incubation period. So there are some assumptions based on all this, and this has been observed. The biggest assumption from my perspective is that the virus has this, you cannot just have one infected population. You should have at least two. Obviously, we want to probably go into some other, to include more population, more than two populations. I do assume that because of the high death rate and high rate of severe symptoms, but the healthcare system might be overwhelmed, or the two people might be also be dying from this disease. So both industries, you know, like being able to deal with the dead, being able to deal with the severely sick, your infrastructure might not be able to take it. So that's why I'm taking it. I have done models which are not dealing just with the classical populations, like say infected, exposed, recovered, susceptible, so forth, but also including say hospitalized population. I'm also including the number of hospital beds being available and the medical supplies to be a restrictive factor. All right, so so when you have this kind of problems, right? There are several approaches to do this. This here is what I'm going to be showing, and what I have shown so far is a classical equation-based approach. I mean, you did see the equations. There's also other approaches based on, one of them is agent-based modeling, and the other one is cellular automata. They're a little bit, agent-based is fairly mainstream at this point, cellular automata it is not. Since we are starting discussing how these models work, I do actually, let me see, I made some kind of visual aid for this, and I'm going to bring it up. So bear with me. So it is an interesting question, how, you know, if we have certain social network of people, how say this virus is going to propagate. And so here you can see, I mean, I have produced some social network here, and here it's not what I expected, right? Yeah. So here we have one person who is who has the disease, and we can see how this actually can propagate over the whole network. So this, what you see right now, it's actually related to the agent-based modeling. It starts with this kind of we start with this kind of picture, mental picture, regardless of the model, but agent-based modeling continues and develops here. With the other models we see, we actually have, imagine that I actually use a certain larger graph here and do some, you know, like I have a larger type of population. Well, I mean, we actually expect certain different homogeneity of, if we're living in certain, say, university campus, imagine that everything we do, it's actually one big village, and we have one grocery store, one school, one factory. So people actually meet everyone is, if they don't meet each other every day, there's a large probability that they, for example, might handle or they have touched something from a person, from every person in that particular campus, village, or whatever. So in a sense, instead of having this, what you see here, and I'm going to reduce this to something smaller, instead of having some kind of social network like this, we assume that we have this kind of complete graph of interactions. That's just cannot be seen, I guess, so I'm going to reduce it. But imagine something like this. Everybody meets everybody in one way or the other. So with these assumptions, the classical models have been made. This is how we're actually doing. Because of this assumption, I'm doing this sphere model, and I'm going to plot it here. So I'm going to take the sphere model, and then I'm going to do the, all right, something here happened. I'm going to evaluate it. So in the equations here, you can see that I have my contact rates, I have my susceptible populations, infected population, and so forth, right? And so, as I said, I actually do think I have two populations, and I want to include the population which has been exposed. And so the equations here become more complicated. These equations here, they come from, they can be done from the perspective of epidemiological perspective, which is classical, developed over the course of, say, between 80 and 100 years. Or you can also utilize a methodology called system dynamics. System dynamics, here, it's actually developed, although it's very similar, it is developed in the 50s. It's mostly for making managerial decisions, and managerial means anything actually. This kind of decisions between different entities which are hard to predict. They are in the scope of system dynamics. So this is what I'm going to be describing next. And so in order to describe system dynamics, I'm going to use a tool called System Modeler. This is just to clarify. It's just, I think it's easier to describe what system dynamic does with this tool. This tool is based on a language called Modelica, which is an object-oriented language for specifying models. I'm going to use, ideally, this is some subject familiar to almost everyone, should be familiar in this presentation. This is how we actually simulate, we're trying to simulate a certain development, software development cycle, and the finding of bugs into the software, how the bugs are fixed and what exactly is happening. Instead of typing in equations and coming up, scratching our heads and putting differential equations, which presumably, I mean, some people just don't have the skill set or don't have the thinking, the background for it. We can actually use this type of paradigm, this nomenclature. We have bathtubs, like what you see here. These are the stocks. You can think of it as a bathtub which gets filled with water. And more or less, this is what this icon represents. So this is the stock of software that has bugs. We have valves. So from somewhere, you know, we get software which is filling out this bathtub. And some of this software gets fixed, and this is happening with certain rates, which is, you can see, it's like around 60–70%. So 6 times slower than it actually coming in. Now we can also simulate what exactly is happening, how this software bugs are being discovered. And this is, I'm using this kind of pulse function in order to simulate something like agile process, like say, which is 2 weeks. And in the first week, the developers are working. In the second week, the testers are testing what the developers did, and they're discovering bugs. Also, there's some kind of crunch time or whatever, some kind of constant function here, which at some point kicks in. And you see these two rates are being summed and fed into this valve. This valve becomes more open, and there is going to accumulate more or less bugs depending on what you see here. All right, so let's actually simulate this. before simulation, I mean, this is the modelical language, which if it's an object-oriented language, this object-oriented language, I'm using a particular library which have extended that object-oriented language to system dynamics. And so now I'm presumably in a position to simulate what is happening here. So I'm going to be, this here opens the simulation tool, which unfortunately does not by default show all of the entities I'm interested in. And so I'm going to be actually clicking here and finding different, so okay, and we can see, yeah, so this is my ratio here, I guess. All right, so we can see that the whole thing is hopeless. The bugs here are being accumulated too much, given this, how this function, this orange function of the bugs discovery, it's happening. It's not, I mean, it's just, I mean, obviously we're accumulating 2 bugs. Now imagine that we actually change our pulse, our bugs fixing ratio from 1/6 or 16%, I change it to be like, say, 80%. All right, so, and run the whole simulation again. I mean, so you can see what now the things are much more manageable. Yeah, you can see again the orange function is, it shows how new bugs have been found. You can see it has this slight jump which came up from this step function being summed, and then but because the bugs are fixed with 80% ratio, then there's some certain steady state here which is observed, and now we can actually also observe certain pattern, oscillating pattern, which corresponds to the rate of discoveries. This is the advantage of using this kind of system. Instead of using equations, instead of doing this in an equational manner, and then writing the, using the underlying solvers, presumably all this can be automated. And now if I have this, if I run the simulations, I can change the different parameters and produce different outcomes. This, of course, this has been used for a variety of situations in this system dynamics package. Very interestingly, let me see. In one of the introduction examples is, it's something obviously related to what we're discussing here. This is the flu simulation, right? And you can see again, we have the immune people, we have the people who are infected, sorry, not infected yet, but they're going to become infected. So from the bathtub, the stock of not infected people, I have a valve which lets the not infected become infected. This valve is being controlled by the infection rates. And this infection rates is being influenced by the contacts and the contraction. When I was showing here in this particular graphs, right? I mean, obviously, depending on the graph you have, you're going to be having different contact rates. You're going to be having different rates with which this virus is going to be propagating. And something is not working here, I guess, but whatever. I'm not going to. Let me see why it's not showing this. Because my graph is too small. All right, so let me make the bigger graph, right? And so again, we actually, so obviously if I start with certain node, and I'm assuming this node is somewhat representative, although it's not, right? So I'm starting with the node 193. I'm actually, my social network imposes certain contact rates and imposes certain assumption of how many people I'm going to meet and what is going to happen. Now, in this model, we don't have such a detailed point of view. We just assume that the contacts, these are the number of contacts which a person can have. And then when they have this contact, this is the probability with which they can get infected. And so back to this kind of map here, what was happening from the infected, we actually, not infected, we become infected. There's an incubation period. This is, so the infected people, they're also exposed. Now here, these are the ones which are sick. And now you can see how the total population, it's a sum of all of the elements in this bathtub. Again, instead of using equations, we can be doing simulations in this way. This is a very powerful, paradigm. In this particular case, you see there's another model which is related, but it's basically about, oh, this is not what I thought. Well, this is about, I guess, yeah, about insects and maybe hosts of the insects. I thought it was about the classical predator-prey model. There's some very interesting, very complicated models about well, these world models. I'm not going to describe them, but for example, this is the so-called world model, and it's simulating certain stuff about the world getting out of resources and etc. I'm not going to be talking about the system model anymore, but I'm saying that more or less this kind of paradigm has been is used. We have the stocks, which we see, sorry, the stocks, these are the bathtubs I was mentioning. We have the valves, we have these rates of changes. And in all of this, you actually can see there always some underlying loop. If I go back to my original example, since it is easier to discuss with the software working. So there's a cycle, right? I mean, there's a cycle here going through the whole point. Very simply, we have the stocks, we have the rates. These functions, they can be something we actually impose, but obviously this can be functions derived from, say, data analysis with stochastic nature, and this can be some probabilistic function. All right, so what this has to do with, say, modeling, and why I'm saying that modeling has been done in the same way and so forth, right? So I'm going to open a notebook here about this, and after this notebook, we're going to be taking questions. So just a moment, let me find it. It was just here. Well, Right. So this here shows the main workflow when it comes to this kind of models. I did mention that there's a bigger picture, right, of doing the decision making and etc. But then what is the actual, small picture about it, right? And so I would say this is it. So let me open this actually as an image. So I have this two infected populations. My population, I have the recovered one, the susceptible, and I have the two infected populations. One of them is severely symptomatic, one of them is normally symptomatic. I have a few models with this. In this first model, which we are going to be discussing, I'm only discussing this first rectangle of this graph, of this diagram. In my second one with hospitalization, I'm actually discussing these two. And my last one with the economy part is taking into account the restrictions from the, how much medical supplies we have, what is the delivery schedule for the medical supplies. And obviously, we have the restrictions of the hospital beds and the supplies being available at the hospitals. So in this first model, as I said, I'm dealing only with this first rectangle in this diagram. So the classical epidemiological models, we get one of the models, like say, for example, the one I'm talking about is this model, is this typical model here, right? I mean, this is one of the models I mentioned with two infected populations. Then we scratch our heads, come up with either we use statistics, knowing about, say, what is the population we model. I mean, as I said, it's like, imagine we model something like a big city in which everybody's using the public transportation, everybody's seeing everybody and so forth, right? So this is, we need to figure out the initial conditions and the populations involved. Then we actually would be interested in certain parameters probably, which we don't know. Initially with this, the coronavirus, the COVID-19, it was not clear what are the contact rates and what are the, say, the infectious rates and so forth. And so so in this model, what I'm going to present, all of them are subject to investigation. So from if your system at hand allows you derive parameterized solutions for the models of I mean, again, I'm already married to this classical equation-based modeling. So I am solving the equations via systems of differential equations, ordinary differential equations. I'm using some sort of, it doesn't need to be interactive interface, but in a sense we are doing that. With this interactive interface, we actually do, we experiment with the different results by varying the parameters. And we are trying to calibrate with real life data. Okay, this was a lot of blah, blah, and I should have probably just show you what is happening here. So this is the parameters I'm talking about. If I increase the incubation period, you know, obviously things change, right? If I increase the infectious period, just decrease it, you know, things change and so forth, right? My population, as I said, it was, you know, 220% of them are being severely symptomatic, but yeah, you can see if I change it to something, to find something smaller, you know, like something bigger, you know, again, my landscape of the solutions changes. So a couple of things to mention here. This is not something you can do with statistics. Statistical methods, they're very good at figuring out steady state solutions. You can use them at steady state solutions. This kind of dynamics and variation, this is beyond the, you know, the methods we in statistics, machine learning, whatever it is. Largely because when you don't have enough data, you actually kind of forced to understand the process more and do some, from knowledge, your knowledge and understanding of the process, make a model like this. And after we have made the model, as I said, it has some very, very interesting and very non-linear type of dynamics. We try to calibrate it. I have taken this data, this was from 2-3 weeks ago. So this data is from Wuhan, no, this is from Hubei. But anyway, I've been trying to calibrate this so you can see some calibrations. The calibrations are wrong, but you know, it is an attempt. And so here it is a very important thing to do, to try to calibrate your models and to see to what degree, how adequate you are and, you know, where things are going. You can see in all these models, actually, there's this kind of peak here. I mean, there's this long tail. We're just not very good at this, but these are also very simple models. So this was probably the first basic workflow I wanted to discuss. I'm going to show, and just for the sake of time, I'm going to show a more complicated workflow, which has the economics involved, and then I'm going to be taking questions. So in this model, the one which is in between, the one which simulates this rectangle and the hospitalization, it's a subset of the whole thing, which I'm going to be showing here. And so what is interesting here is that actually I have to say I'm missing a step here. And before doing that, we need to discuss a very important case in which we are going to be discussing quarantines. And in order to do the quarantines, I need to actually go to the model, which is, I mean, this is just a separate implementation, which I didn't move to the big model. But in this model here, we're going to, which is for these two squares here, sorry, rectangles, the infected population and the hospitalized population. I'm going to be including the hospitalization, and I want to play with the quarantines. Now, this is the big picture of how these models relate to each other. I have a basic SIR model, which is being extended to have two infected populations. Right now, we're discussing this one. After the second part of this conceptual section, I'm going to be talking about the multi-site expansion and how this can be applied to USA. All right, so what is happening here, and I'm going to evaluate everything, is that you can see that I included the hospitalization of so I have a population which is with the hospitalized people. Also, I have a number of hospital beds. If I don't have enough beds, I just don't hospitalize people. Another thing which can be seen in this diagram, I'm only hospitalizing severely symptomatic people, right? The ones which are normally symptomatic, they're not hospitalized. Only the severely ones hospitalized. Again, this can be seen in the equations here, but the ones which I'm taking in, they actually, this parameter here, which gives me the severely symptomatic population, I'm taking it from the exposed population. All right, so what I want to do is to actually, my contact rates, if I put a quarantine, my contact rates are going to change. They're going to be decreased. And so this is what we're going to be playing with. So in this interactive interface here, I am basically starting the contact rate at different points, right? If I don't, this is how this is going to look if I do any quarantine. But if I change my quarantine to start at day 65, I mean, we can see that this is actually flattening the whole curves of exposure, infected and so forth. So my other thing is that how many beds do I have up in the population? Again, I'm going to imagine we don't do quarantine. In America, we have like say around 2.93 beds per 1,000 people, but imagine you had 20, right? So you can see what the effect on the bed, the number of beds we have, it's somewhat small. And although it's observable, it's actually not, it's not sufficient, not enough. Another thing we see here, and I'm going to go to the normal number of beds, normal number of hospital beds. If the quarantine starts at day 65 and it's long for 8 weeks, 56 days, I'm going to produce one kind of profile. If I make it 2 weeks, I mean, you can see it has some effect here, but this effect is not as pronounced, right? So obviously, like maybe I should go for like 4 weeks. Yeah, same thing. I mean, we actually see that there's some mitigation, right? But it's not necessarily going all the way through. Now, if we really want to flatten the curve, right? Something like say, 56 can work. And if I just imagine that I just do total lockdown for the rest of the year or something, right? Then it's very flat. So the other thing here we're playing with is what is the interaction fraction? What is the interaction fraction? How the contact rate changes. If I put if the contact rate is the same, right? So people in a lockdown, but they just don't go to work. They still go to the beaches and meet otherwise and whatnot, which apparently is happening in US. So then actually, yeah, this is just ineffective. So the question is to what degree you decrease the contact rate? Is it like say 10 times, is it 100 times, right? And or is it like is it say something more like say only half, right? These are very different scenarios, as you can see, and different countries, they committed to different type of enforcement or not enforcement or whatever of the quarantine, how the quarantine is being conducted. After we have made this kind of parameterization of our model, it's a very good idea to see how it's going to how the population is going to change when we actually experiment with the different parameters. And you can see here that starting basically, if you start your quarantine too late, the effect is not that big. Actually, let me show this here in a different manner. So let me do 20 and maybe I'll do 100 days. So yeah, I mean, we can see with 50, we moved it. With 70, yeah, we have some sort of, small decrease, but it wasn't moved. And now with 90 is actually, nothing, I mean, we didn't actually produce anything. I mean, if I put, so 90, just a moment, if I do, say, if I don't do quarantine at all, right? Like if I do this, say, after 300 days, I mean, you can see basically what was with 90 days and 300 days, they basically coincide. The other thing is that there's apparently a window in which you can apply it. I mean, if you apply it too early and if you apply it too late, it's actually still not that good. So again, you know, if I actually do, so if I put here 65 days, which I was putting earlier, right? We should, ideally, we should see, you know, how for day 65, I actually have a more pronounced effect than 50. It's actually, although it's 15 days later, it's actually more preferable than applying it at day 50. This type of scenarios, this type of scenario playouts are extremely important, obviously, for planning purposes. And this is how we actually can figure out what to do next, where to go, what policies are feasible, what is going to be obviously the impact of this kind of strategies on different economical parts. In the first situation, and I don't think I have time to describe the economical model, but in the economical model, I'm just going to outline it, the one which I was showing earlier, which has the hospitalization, also the delivery rates and etc. I can actually see in some of the simulations here that the frequency of delivery and the number of hospital beds, they do change quite a lot of certain behavior and parameters. So I'm just going to outline it here. But for example, I have been trying to hospitalize some people, and this profile here of the hospitalized population, the orange one, was on a verge to look like some of these populations, like the infected ones. It was trying to be something like this. But well, we didn't have enough hospital beds, which we see here with the blue line. But another thing we didn't have is medical supplies. In my equations here, I do restrict, let me bring it up. I do restrict the hospitalized people both by the hospital beds and by the hospital medical supplies. These are the medical supplies at the hospital. So this is the single site models, and we are going to see how these single site models are going to be expanded over a large region, like say US or Germany or whatever, in the next part of the session. So as I promised, there are some questions here to be taken.
Yes, we have 3 questions, Anton. So I believe the first one you already answered. It was about how was the infection rate estimated, but you already show how you're parameterizing it. So you can change it.
Right, correct. It's a calibration process. This is when you do this kind of modeling, right? I mean, calibration process is extremely important. And so here, like in any of this, let me zoom this a little bit. It's after you have selected, like which I did, I have selected, say, what I'm doing meso level type of compartmental model, right? I need to do some initial calibration. This is just during the modeling process to kind of see, can I actually model the reality at least to a point? And is this model at all feasible? All these models, initially, they're not that good. Every model is a caricature, right? I mean, of the reality. The question is, can we actually, if we put enough work in it, can we actually make it better? And the idea, of course, is not just to be able to predict, but to be able to change the parameters in order to see the scenario play out. For this, much better calibration has to be done. And in some situations, for example, you might prefer, like say, imagine something like the rotavirus, which targets children between 1 and 5 years old. Then this is your most important population to calibrate against. The older people don't get that much affected by it, and even if they do, to some extent, they're a small percentage, and the consequences are not as severe or not as dramatic. For children, it's like literally a life-changing event. So we target certain population, the model to be calibrated against certain population. So this type of work I showed, like changing different parameters, seeing the sensitivities of the solutions based on the parameters, this is systematically done in order to adopt a certain model. The same model can be calibrated in different ways for different type of decision making. Yeah, right. I
Okay.
mean, you said I answered it, but yes, I would like to reaffirm my answers.
Yes, yes. So the next one is kind of related. It's about if you are representing uncertainty in your parameters.
Well, this is, I mentioned this earlier. The uncertainty right now, for example, in the models I showed, I can, let me see, not this one, the previous one, right? Let me show it to you how it's happening. So when the model has been prepared, I mean, you can see initially I have certain functions being adopted. Let me zoom here. But now I'm actually taking certain focus parameters. This is my, say, contact rate. And you see I replace it with a function. This is the piecewise function, which simulates the quarantine starting date, the quarantine factor, reduction factor. And this is the, given the quarantine length, what is happening, but basically the contact rate has been decreased to say 0.25 or whatever it was, what we see here. Now, obviously, instead of doing a piecewise function, I could put any stochastic function here. So although the model is deterministic, you can, if you, and this is something I mentioned earlier, we actually, from analyzing the data, we actually can figure out what are the actual functions here, and then feed them to the model. Like this particular, I mean, it's always a good idea to go to see this kind of models from another perspective. So imagine that instead of coronaviruses, we actually look into dog adoption rates, right? So for example, here, this is like, where you can see there are some people, this WDR is like dog wannabes, so they, for some reason, they increased from 3% in the population to 6% in the population. And then what is happening to the food demand and so forth and etc. Right? Now you might ask me, fine, but how do we know, how can we estimate the demand? And one of the ways to estimate the demand for dogs or pets is to look at, say, pet licensing data. And in the pet licensing data over the years, this is from Seattle, I mean, I can see what they sound stochastic trends in some, okay, so here, right? So, okay, so I see how this has been looking at into different years. And then over the years, I actually, and this is something I've discussed in previous presentations in this meetup, using quantile regression, we can actually do extrapolation of the signal. And so this is what is happening. Knowing what happened in years 2019 and 18 and 2019, I'm extrapolating what is going to be happening in 2020. This now, I'm going to be using this as my demand curve. Instead of this step function here, I can actually put this demand curve. All right, so yes, this is how we can introduce stochastic elements into the models.
All right. We have two more questions. They're very specific. There's about how would the model react to some changes in the parameters. One is, what about the effect on the graph? B, if average incubation increases, say, 10 days as opposed to 6 days. So I think this is more about running the model with these parameters and seeing the outcome.
Right, yeah, I mean, it's not, I mean, ideally, you just get this notebook and you can experiment with whatever, parameters you want, right? I mean, basically I changed it. I'm not sure which parameter I was supposed to change, but yeah, I mean, if I want to change the average infectious period, like make it longer, like if it is, say, 80 days and it's not included, since I say 80 days, let me actually do this. So where's my incubation period? Okay, they're all capped at 60. Let's do them actually capped at 100, right? And so here, if I change this to 80 or 70 or whatever, right, what is exactly going to happen? If my infectious period is also long, I mean, obviously the whole thing is going to be very different. The other way around, if I, for example, change my contact rates and, to something else, I mean, I might be asking myself what is exactly happening and so forth, right? So yeah, I mean, this here, ideally, I didn't want to overwhelm, because this is a presentation notebook. So I only extracted certain parameters on which I want to focus on. And I have decided this, which is a fair amount of parameters, but at least in principle, I can take everything here you see as rates. I can like say mortality rates and etc. Like I didn't include it in my, they're not here, right? But I can include mortality rates. I can include some other elements here in order to do the simulations. The other thing is, but and this is interesting, which I didn't explain, but I do actually have a hospital beds change rate, because obviously the hospitals, I didn't model the population of the physicians and nurses in the hospitals, how they get affected by the virus. They obviously have probably different contact rates. They also, like the rest of the population, can get infected. They have mortality rates and so forth. But instead of that, I'm actually saying I can model what is how my beds change. My hospital beds number changes throughout the disease. And again, this can be done through whatever functions I mentioned. But for example, imagine, usually this is going to be decreasing because other people are going to be coming and some of the physicians and nurses are going to drop out due to infections. But if you actually build hospitals in between, and this is what I was trying to show earlier, if I say increase my number of beds to be, you know, from 3 per 1,000 to 10 per 1,000, I can actually see what this actually does affect the whole system. More or less, this is what happened in China in Hubei province. They built a few hospitals fairly quickly, maybe not overnight, but within say a few days, they actually built new hospitals.
So you just answered one of the other questions, which was about the infection rate among healthcare workers.
Right. I have to say that's a very good question, and it should be done. Right. If I go back to this diagram, this, you know, healthcare workers, I just didn't include them in the model. Right now, I would say fairly inadequately, they're basically done through the hospital services and through the changing of the hospital, the number of beds changing rate. That's simply not adequate. Although with this, especially if I program medical supplies in the economical model, I can consider the care being given by the physicians and nurses to be a resource, right? Like something like medical supply. So instead of actually looking at the population who lives in the hospital and gives care, I'm actually saying I have this kind of stock of number of hours to be given by healthcare professionals. This actually is not necessarily a bad perspective. It might be actually more suitable under certain conditions. Like you basically have certain, you know, I don't know, like a storage of man hours to be given as healthcare, and that depending on how many physicians and nurses you have, this changes, you know. And obviously we can say, imagine we import like what happened in China, right? I mean, if some of the physicians and nurses become sick, they actually can supply physicians and nurses from the other states of provinces of China and so forth, right? So in a sense, this can be modeled in that way. From that perspective, although the models become fairly complicated, and especially if you want to scale it to make a multi-scale model, they become very complicated if we increase the number of the populations. I would rather be increasing if I change my populations, I would rather break them by age. Like say, you know, children, you know, young adults, and, you know, old people.
Right. We have another question about asking you if you could elaborate the part of the model that shows the quarantine won't be as effective if it's applied too early. If you could explain more.
Well, I mean, you can see that obviously if I change the incubation period and the infectious period, right, things change, right? So because of this, I mean, if I actually want to, you know, these numbers here, if the more precisely they're estimated, the better we'll find out what is the best time to start this incubation period. Sorry, to start the quarantine. I mean, you can see with the numbers I changed right now, which are not, as far as I know, they're not the ones which are happening. 65 stop being an effective time, right? It's like around say 110 or whatever. And you can see another thing here. There's a very non-linear dependence, right? I mean, you can see because it's 56 days. Actually, let me do it just 60 days. It's easier to do the arithmetic, right? So you see it starts at 110 and it is long for 170, right? So it stops somewhere here. So fine. Now, if I just increase it, right? Increase it by say, I don't know, this is like this increment here, it's inadequate. Bear with me, I'm just going to fix this because, which is not a big deal, it's just, I don't, quarantine start days, 0.01, it's just not adequate. Okay, so what I was doing here, it was say 45, right? And I was doing 100 days and I was doing some 60 here, right? Something like that. And apparently I forgot what was the other number here, right? But okay, let me actually start searching again. So there's a very some of this is very sensitive. I mean, you can see if I do some small changes here, this might actually change fairly dramatically. Okay. Yeah, well, yeah, I mean, yeah. So there's a. This is in economics, you can hear this as a price elasticity in which, you know, like say certain hotel room costs $500. If you increase it or decrease it by by $10 or $5, like within a range between $480 per night or, you know, $520 per night, you don't change the number of people who occupy the room. But if you go below 450, this is apparently a psychological threshold, you start to have like massive increase of the number of people who want to go. And so similarly here, there's a certain spot which is very sensitive to the starting date. So it is very important to have to have good estimates of what are these incubation periods and infectious periods. If you don't have this, then your other approach is to just use long you just use long quarantines, which is of course also unacceptable, especially if people are at home, and then, you know, you cannot do economically, they're not going to be productive. So, you know, there are this kind of trade-offs. That's why I'm interested in not just in the epidemics modeling, but also what is the economy behind it. And so this is actually what I'm going to be discussed next.
Yes, and just a reminder, Anton has published the Git repository for all these notebooks. So you can actually download them and use them. And Mathematica has a trial. If you don't want to pay the license, they do give you a trial the system, and you can use it for, I think.
And there's a Wolfram engine for developers, which is free. You can connect it to say Jupyter notebooks or whatever if you want. So I mean, in general, yes, I mean, all this can be done. System Modeler, which I was showing earlier, that's an independent piece of software to a large degree, but it was purchased by Wolfram Research. The System Modeler group was purchased by Wolfram Research at some point. So it's like a first-class citizen. Mathematica is a first-class citizen. If you decide that System Modeler is the way to go for whatever projects you do, you don't need to buy Mathematica. You can just use System Modeler. System Modeler generates C code, which you can put, say, in Raspberry Pi or Internet of Things or whatever it is. I do strongly advise people who are more technically inclined or software engineering inclined to look into the system modeling. In my GitHub repository, you can find like this notebook, the basic one. I'm going to upload the ones with the quarantine changes, but you can find them here. They're without output. They're very lightweight. You can see 95 kilobytes. You can always find them. There's also like the things you see here. They're basically explained. I do have markdown versions of those. So you can say the one I was just showing, I mean, you can actually go on this GitHub repository, see what it is, and presumably all of the code here and the different calibrations and whatnot we're discussing is here in Markdown. Even if you don't want to use Mathematica, you can still consume this in one way or the other. All right, well.
There's a final question, Anton, is about how you estimated infection rate given the largely non-symptomatic population. So for people that have no symptoms, how are you estimating the infection rate? I think this is associated again to the way you're parameterizing and then calibrating.
Yeah, I mean, there's no, right. I mean, there's no, of course, you're scratching your head and you're saying, look, I need to figure out how this parameter is being changed. So I'm going to go back to this basic model or whatever. I mean, in some sense, you see, this is what I have been doing here. Apparently, first of all, just a moment here. And so I'm going to return to that thing, right? So what is going to happen? This was pretty quick, right? So what is happening here is that, I mean, I choose some parameters. How adequate are these parameters? 5 days, 26 days. I mean, they're obviously not very adequate. If I decide, I might actually, like say, look at say 15, and also I have 6, right? And now you see, but the people who provided this data, I mean, you can see the way this data is structured. They have been telling me the recovered cases and the deaths, but obviously this happened sometime before that. So when they saw this disease, they didn't know what is the incubation period and what is the recovery period, right? So I mean, in a sense, I have to scratch my head and basically pad this data with zeros. This is what is happening here. I'm actually, actually, let me go to the interactive interface. I'm actually saying how many, how much, what is the offset for this data? And something is not, but you see, I mean, if I change some of these assumptions here, right? I mean, this data is going to be changing. Sorry, I just need to do this to say 100, at least 200, I guess. And so by varying the different numbers here, right? I mean, I can produce better or worse type of fits. So I mean, apparently here, you see, I'm changing the initial population because my model is so inadequate, but actually I have to change the initial population quite a lot. Now I can actually try to, I missed it again. Let me see. I can try to do this, right? And basically figure out some stuff here. And now, okay, whatever, right? And then after I fit it, I can try to play with some of the rates here, right? Do something like say this, apparently this was not good, well, whatever. But my point is, I'm doing this manually. This can be automated. I didn't do it yet for this type of models, but say in general, you can automate this calibration. You can just make it. I mean, you can imagine if you have a, ideally you're not just doing a blind search, right? You're not just doing a bunch of parameters and then evaluating the models over these parameters. You actually have some kind of guided, idea what kind of combination of parameters to look for. But yeah, I mean, you can presumably calibrate the models in this way. All right, I guess we have, Luis, how much time we have? Like, is it 10 minutes or is it or you can go further than more than 10 minutes?
We can go more than 10 minutes if the audience wants to stay, but we have at least 11 minutes at this moment.
Okay, right, great. So, all right, I am going to go back to this mind map, this one, right? And so what I'm going to be talking about is how we do multi-site extensions of these models. And I'm going to do this very quickly. So again, what I was discussing is that we assume that these models, they work for there's some sort of artificial assumption, but this is in an area which everybody meets in one way or the other, meets the others, like either they have touched the same doors or the same groceries or the same boxes or whatever it is, or, they basically, even if they don't talk directly to the people, we actually have whatever this contagion, how it is propagating, we actually through contact services or so forth, right? People are being able to transmit this disease in a relatively this kind of complete graph manner, right? Like the one I was showing earlier. Let me see, do I have this notebook here? You know, so and no, I don't want this, and I guess I closed this already. But anyway, that actually assumption it's not necessarily holding. So I'm not, you know, instead of having the complete graphs here, we most likely are going to be having, you know, we're most likely going to be having something like this. And not just that, but in a sense, there'll be some kind of communities. And let me see, can I do this here? Community graph plot. Right, just an illustration. Don't take it too seriously. It's just an illustration. But I mean, basically, if I look into what's going on, right, people basically will cluster, right, in some way or the other, right? Be that because of accessibility or for whatever reasons. Like, I mean, one easiest way to imagine clustering like this is because of distance, right? Like, say, different neighborhoods or different cities in some country, or, you know, like different states in US and so forth. So the idea is that we actually apply our single site models to the different, sorry, some alarm here. We apply this kind of models to a single site, and then, but what happens if we, on all of these sites we found, we apply these models? How these models, how the results between them can communicate between each other, and what is the global picture after we do that? So this is what we are discussing next. This is this multi-site extension. I'm going to show it in two ways. And so one is with using, let me see here, using a regular graph. So imagine this is very artificial, but it is actually, it can be used to build confidence in our model. So I'm going to evaluate the whole thing. So imagine that my sites are like this, and you can see that, say here, nobody is traveling to site 1. Everyone is leaving site 1, and they're trying to go to site 84, right? You can see how all the directions, you know, all the horizontal directions point to the same direction, all the vertical ones to the same downwards, and left to right for the horizontal ones. So now what we are going to be expecting here, but if I have a good way of approximating the traveling flow from through this graph, the whole thing is going to look like a wave. So what I'm going to be doing on each of these disks you see here, numbered by integers, I'm running the single site models. The single site models, one of these classical models. And then I'm letting them actually exchange populations. So this, I think I evaluated it. This is exactly what is happening. You can see how, maybe I should do random sample and I should sort my sample. But yeah, what is happening is that the ones which have smaller index, they get the evolution of their populations earlier than the others, right? The ones which are like with high index later than the others. Again, this is something to be expected because the way I did it, I put nobody was infected. I only put one infected person in site 1. This is actually probably seen here. You can see how I made site 1 to have one contagious person. What is happening when I have this kind of model table form, right? I can actually extend it. I can make a copy of it. Like, say I have a function which tells me not this, not model identifier, right? And say I'm doing 1, and actually I'm going to do something else here. Let's say it's not 1, but it's something in red and this, right? I mean, you can see it's just the same equation, same thing, everything, but I just put some, unit, some kind of identifier here. And of course, I can do this, also like that. Now I have, having this functionality in my framework, I can, what is happening here is this single site model is being, seed model is being propagated through this grid matrix. This matrix, it comes from the traveling patterns which are between the nodes. So I'm kind of rushing here, I guess. But this matrix tells me the traveling patterns between the nodes. It's very simple. It's derived what people from, say, this node go to this node and to the other one, and that's it. This is what you see here, right? Anyway, after I have done this, yes, this basically with my artificial construction like this, I would expect the nodes with higher index to the evolution of infected, recovered, and so forth to happen later than the ones with the lower index. And this is what I observe in my random sample results. What I also would expect is that my ground zero, right, my patient zero who starts at 1, I'm going to be expecting some wave through which this is being propagated. And this is exactly what you see here. So this wave, the front has high contrast than the tail, because well, if we look at these plots here, you can see how this the gradient here it's steeper, and the evolution here in time it's much more like round tail or whatever. It's like longer tail. It's not as steep. It's not it's developing slowly. If I have put something, if I made this animation with, say, instead of my infected population, if I made this with, say, my exposed population, this wave is going to be sharper, because again this is something. It is going to be sharper because when I look at these plots here, right? I mean, I have this sharp wave. So I have plotted here, by the way, I have plotted the first one and the last one, and you can see nobody's traveling to site 1. That's why the total population is decreasing, and everybody is going to site 84. So the total population is increasing. And the evolution, as I said, happens much later than the first one. So, all right, this actually, we're doing this in order to build confidence in our model. So in a sense, we actually know that we have a model which actually can work in that way. And you can see that if I look at the infection populations, the curves of the different sites, how they look like what I expect. But if I sum them, if I make the infection population for the whole set of nodes, for the whole rectangle, right? You see how this is actually much more symmetric. It exhibits a much more symmetric nature. This actually might be hinting that this is probably the reason we cannot actually do a very good fitting in this model I was showing earlier with Hubei, right? I mean, I guess, fine, whatever, let's actually evaluate the whole thing. And so, yeah, I mean, you see how this red dots, which come from the actual infected cases measured, the whole thing, it's much more symmetric according to, around some axis. So this actually can be one way to address this kind of parts purely from a fitting perspective, is to have a model which is special in this way. We have only 1 minute, Luis. I guess I'm going to continue with the big model and for 1 minute, or what?
Yes, no questions so far. So I please continue.
All right. So in order, we need to. I'm basically, well, I'm not going to go through the whole thing here, but there's also, of course, you can tell me, regular graphs are fine, but this was just a regular graph, and this kind of wave, you can simulate it in different ways. Well, that's why I'm using random graphs. And these random graphs, I mean, here you see a very small graph, but we can do simulations with the random graphs and you get some kind of meaningful results. I'm going to go to the simulation I did over US with certain certain conditions. It's a different simulation. This here, what was happening is it's not the one derived from the airline traveling patterns, like traveling by air. When you impose a certain quarantine, people are not going to be traveling by air anyway. So I'm actually using a different, I'm making this tiling of US. In each of these tiles, it's basically a region on which I'm going to apply my single site models. And then I actually impose certain interaction between them, which is based on, let me. So you can see this graph here. When two nodes are connected, this means that, you know, people there exchange populations. And I make the exchange of the populations proportional to the total population between the sites, like say 12%. Every day I expect say 12%. If there is no quarantine, 12% to move between them. The empty sites, this means nobody lives in this area, so whatever. So all right, so this is my graph, how it looks, how it, you know, what is the, if I look at the traveling patterns, the arrows here, they definitely show what is the traveling pattern, right? And basically nobody is flying. The government has forbidden all flying, and people are just, you know, basically traveling by car or by train or whatever between these different nodes. And then we're making the simulations, and we can actually see, I made this with the economical model. What is interesting here is that I can see, like, for example, initially I was thinking, oh, well, the deceased population is quite, the deceased infected population is quite large. But if you make a ratio between the total with the deceased infected population predicted and the total population, it's actually on par. It's 1.5%. It's on par with our assumptions for this virus. The other here is that you can see how the hospitalized population, they were on the verge to become, the hospitalized population, if there are enough beds, it should follow the profiles of the infected severely symptomatic population. It should look like this. And you see that it actually kind of tried to look like this, but it got cut out because there is not enough beds. And so there's other effect here. This here, it's actually when the quarantine starts. I run this model with a quarantine that starts from 65 days and 56 days long. So if I go back to this a hospitalized population plot, I see this around 65 and then plus 50, 60, it's like, you know, here. So this was the effect of the quarantine. And then after that, of course, the demand for hospitalization rose. And this is my prediction for it, given what is going to be happening with the, you know, with the knowing what are the restrictions for the beds in US. Obviously, we can, very important economical questions is the medical supplies, you know, how they're produced and etc. Here, these are the medical supplies at the hospitals, for all hospitals across all sites. And these are the, and I compared this with the actual hospitalized population. Of course, they're going to be mirroring each other, because at some point, the hospital supplies become a decisive factor. Do we hospitalize someone or not? So this here, I would say more or less this is what I wanted to describe. There's some further statistics here, like say this particular model, if I want to visualize it further, like say I can show, for example, what is happening. You know, I started my initial condition actually somewhere from Mexico. I mean, I choose them randomly, but this is what you are seeing here, right? So actually, let me see. Maybe you can see this in this animation. So in this animation, we're going to see how the initial infection from here propagates throughout the US, right? And so this again, this here, it's normalized. It's normalized by the population on each site. That's why it looks like a nice regular wave. If we don't normalize, if it is absolute, it's going to be just, you know, like what you're going to see here, right? So anyway, now if I want to see how is going to be my 3D distribution look like, and how it's going to be mapped across the different when I change my when I change my global conditions, right, sorry, when I change my time in which I'm observing what's going on, I want to see, say, the deceased, infected population, how it mutates when it comes to different, at different times. And so this actually became a worse plot. Let me see, can I do this? Yeah, okay. So I'm not going to fiddle with it too much because of the interactive part, but yeah, I mean, I can see how my initial infection started here, and presumably I'll be seeing how they start to propagate throughout US. And then the sites which have quite a lot of population, which you can see here, this is a histogram based on the population, they actually, yeah, then they become dominant here in this global representation of the aggregated over all geosites of what are the infected populations and recovered and so forth. So I would say this is it. I mean, the model, my plans for this model are to, yeah, you can see here, is to make it more representative and more tunable, and to play different scenarios at with different starting conditions, different initial conditions, like say this New York data with the known death cases and known infected cases. I want to feed them to be parts of these models. And then when you look at, say, one of the plots here, right, this tooltip is telling me that in this particular site, 294, the total population was 300,000, which, say, if I go to Miami, right, this is going to be like 6 million or something, right, or 4 or 5 million, yeah. So, all right, so I can also, instead of just initializing it with the populations I know at those sites, would be a good idea to actually put the number of infected people and the number of dead people and so forth, and actually make a more representative simulation. This one here, it was a very artificial one. It was just picking one of the, it's just trying to make a nice animation, right? I'm picking just one entry point, and this from how this entry point, how things are happening. So, all right, the big part of this, I would say, I really wanted to discuss the economical impact more, but we have been doing this for more than 1 hour and 40 minutes, so I'm going to stop and some questions to take.
So we don't have questions at this moment. I think you answered them already. We have few about how would being that the rates are not uniform in different sites, how would that be propagating, etc.? So
very good question.
You mention it.
Yeah, a very good question. It's the same way you can see when I initialize my model here. When I initialize my model here, I actually can specify specific initial conditions to the different models. As I mentioned, each of these models, my seed model, right? I'm actually this one, right? I'm actually making it to be with this model identifiers, right? Like say my model, right? And so if I do that, and again, if I just do, right? I mean, now if I want, I can change the rate. I can change the mortality rate for this site. If this was, say, site number 294, right? Whatever it was for, whatever it looked like, right? I mean, say the rates in, actually, let's be a little bit more specific, right? Because New York was very heavily hit, as we saw from the New York Times part, right? So you can see here, but say somewhere here in these sites, right? Like say 295. 295, they actually, if I look into them, I might say their contact rate is very different, because in New York, people using public transport, they're much more reliant on public transport than say any other place in US. There is also, the mortality rate might be different because of whatever, different demographics or pollution or whatever it is, and so you can, but you can see here, for each of these models separately, you can change the rates. Right now, I'm specifying the rates globally. I'm specifying the rates globally in this seed model. It is here. And when I propagate or when I extend this seed model, then whatever quarantine specifications I had, they were replicated. But I can actually have quarantine regime, which is different, starts at different times for the different sites. or I can have, you know, different, as I said, mortality rates. I can have different anything, you know, any of the parameters you see, like incubation period, infection period, can be changing from the, you know, at the different locations. This is also one of the ways to probably model or take in the way the virus mutates and how this impacts the population. Although that would be probably a whole new set of models, how, for example, the mutated virus is going to be included into a model like that. But then definitely all this, imagine that all this contact rates, death rates, and etc., they actually do change quite in time. So you need to take it into account. Is it because of the geographics, or is it because of the genetics of the people in the geographics, demographically? Is it because of the other environment situation there, like say air pollution, or, you know, like certain other qualities, you know, of the environment? Or is it because, say, the actual strains or whatever of the different of the virus, you know, in question, they're actually also mutating?
Great. There is a final question, Anton, from Ron. He's asking, given your work on this so far, what do you think is an appropriate quarantine duration? So I think that's
oh no, I really have no idea. I mean, I have played with different scenarios, and, you know, this might seem like like trying to get out of responsibility, or trying to get out of like easy way out answer. But as I mentioned, this is about making the tools.
Yeah.
Every day I hear some kind of new estimates, and from the team of people I work with, initially at least, a few of them were quite enthusiastically calibrating the models. The calibration of the models itself, it's not a trivial task, and it is something, in some sense, lectures like this, they're also recruiting lectures for me to get people to either get data for my ambitious plan. I actually, because I'm much more interested in doing this, doing the epidemics modeling with different data to actually get the different matrices for the different data. But I do actually want to make also the economic part. And so, yes, the calibration for this, it's extremely important, especially if I just don't want to just do qualitative modeling. I mean, you can qualitative behavior studies, which we just saw. Yeah, they're useful at least to a point. We kind of know what would be the challenges, but then in order to make quantitative results utilization, we need to make sure that our models are calibrated correctly, and that's why we actually need to do, we need to ask ourselves different questions. Is how the reality is described, how well, but how we declare victory, what are exactly the proofs for this, and so forth, right? What is the testing paradigm, who we need to convince, and so forth. This is my answer, which is basically a no answer. I'm just saying, yes, I'm aware that calibration is important. I have played with different calibration kind of things. No, they don't. The simple answers are most likely not correct.
Right. Well, Anton, thank you so much for this presentation. It has been
yeah, thank you for hosting me. Yeah.
Yes. Thank you, everybody, for attending. As I mentioned, this has been recorded, and I'm going to be uploading it to our YouTube channel. You please follow the Meetup site. I'll be posting there the address of the video, and also stay tuned for the chat platform that we'll be using. I'll be sending emails to our email list with the specifications of how to use the chat platform. Thank you, everybody, for coming. Bye.
Bye.